All right. This is going to be the fourth and final part of chapter 17. Before we get into reactions of aromatic rings, that's chapter 18, we're going to look at a very specific type of reaction at the benzylic position. Now, we talked about this word right here when we talked about nomenclature, when we looked at phenyl versus benzyl groups. The benzylic position is the carbon that is adjacent to a benzene ring. Now, it can be a CH3, it could be a CH, it could be a carbon. It's whatever carbon is next to a benzene ring. Think of it like the allylic position being next to a double bond. This gives it special reactivity. And the first reaction is actually really pretty cool. We're looking at oxidation. Now, this is a reagent that you should have learned about in Organic 1. If you did not cover alcohols in Organic 1, it might be new to you. But this reagent right here, it's also referred to as Jones reagent. For the life of me, I don't know why I don't write Jones reagent. Seems like Dr. Jones would want to do that. But I always write out sodium dichromate, H2SO4, and H2O. This reaction also works, right? We're looking at strong oxidation reagents, right? So like a PCC is not going to work. Sodium dichromate in acid with water is my go-to. One that you might also see in some of your practice would be something based on KMNO4. I can't remember if that is in this slideshow. Yep, there it is. That one will often be paired with water and heat. And then you usually need an acid workup to protonate the carboxylic acid product. But these are the two reagents that you might come across. You can also, you might also see Jones. This is the one I usually test over, so make sure you know that set of reagents. Now, when you first learned about these strong oxidizing reagents, you learned that it could take something like a primary alcohol, and we're going to have these strong, one of those choices, how it could take a primary alcohol and make a carboxylic acid. Now, when you apply those reagents to benzene, nothing happens. If you apply those reagents to an alkane that doesn't have an alcohol, nothing happens. But there's something special about that benzylic position that does react with sodium dichromate, that does react with these strong oxidizing conditions. And it allows us to oxidize that carbon all the way to a carboxylic acid. And what's even cooler is it doesn't have to be a methyl. It can be any R group as long as there's one hydrogen on it. All right, so any benzylic sp3 carbon, right? So if you bring double bonds into this, all bets are off. Carbonyls, all bets are off. But if you have a benzylic carbon and it's sp3 hybridized with at least one hydrogen, it will convert to a carboxylic acid. So you see the example over here. You have a butyl group. You could have an isopropyl group. It has at least one hydrogen. We'll put those strong oxidizing agents here. Now, this is just my shorthand for strong oxidant. This would be the reagent that you want to commit to memory. Right? The isopropyl group has one H, so it would be converted to benzoic acid. If you have something like tert-butyl benzene, this will not react. There is no hydrogen there, so this does not work. This could even be, it could be a ring right? Let's say we have a little bromobutane on there. Not bromobutane, cyclobutane. We are using our chromic oxidizing reagent. There is one hydrogen. It will be converted. One way I like to test you on these questions, you'll see some in the practice tests. This is kind of like hydrogenation. You typically have these reagents in excess. So they're not selective, and so they're going to oxidize whatever benzylic positions are around. So I might give you something like this. Maybe it's got an isopropyl group, and maybe it's got this substituted group. I'm going to swing this around. But if I treat that with sodium dichromate and acid and water, then I need to think about which positions are going to be oxidized. Well, the propyl group, it's a CH2 here, so that one would be oxidized. Isopropyl, we talked about that. That one would be oxidized. And while this isn't a T-butyl group, it's got that substitution around the benzylic position like a T-butyl group, it would be unaffected. So sometimes I like to mix it up where there is a reaction on some but not on all. So that's another problem type you can watch out for. Again, KMNO4 does the same thing. The issue is that winds up giving you the benzoate ion. And so that second step of the acid workout is just to make sure that you have it protonated. Other reactions that occur at the benzylic position, the addition of bromine to an alkane piece using NBS and heat or light. Now, their example is fine, but I want to use a different example to point something out. Now, if you're just dealing with an alkane, you usually put, and I'm going to use light. I usually use light to initiate this reaction. I typically would expect the bromine to add to the most substituted position. And the reason for that is because that is typically the most stable radical. Because remember, this goes by a radical mechanism. However, and it depends again how organic 1 went for you. Maybe this was explained, maybe it wasn't, maybe it's just a reminder. But primary, secondary, and tertiary aren't the only things that you can list in terms of stability. All right, so we're looking at stability of radicals. It's the same trend as the stability of carbocations. And so the least stable is going to be the methyl, right? And as we add more R groups, it gets more stable. So CH2 with 1 R group, CH with 2 R groups, right? C with 3 R groups. That's the trend in stability. Something else that you have to add in here, though, what else can stabilize an intermediate? Well, resonance can. Allylic and benzylic positions, that is horrendous. Let's fix that. Here we go. Allylic and benzylic positions fall to the far end here. An allylic radical may be more stable. For instance, if you had a secondary allylic radical, that would be more stable than a tertiary radical. A benzylic radical is one of the most stable because that kind of the stress of the charge in a carbocation or the stress of the radical can be shared by multiple atoms. So in this scenario, I would expect the bromine to add to the benzylic position, even though it's secondary, and there is a tertiary position right there. The benzylic part makes that even more stable. You can do any other, this is just review of organic 1. There's nothing really new other than it is on the benzylic position. If you are going to do a substitution, because you can't do if you're going to do a substitution on a compound like this, same rules apply. Why does this go SN1? Because this is a tertiary alkyl halide. If it is a primary alkyl halide, then, and you have a strong reagent, then you get an SN2 reaction. Neither of these are new. They're just review. You're not likely going to be tested on them specifically from me, but it's nice to see them before we get into synthesis sometime next week. As far as eliminations go, it just depends on what else is attached to it. You can have E2 or E1. Again, this is Organic 1 review. And this is, I love how Klein makes these summary slides. I don't know that this is my favorite for Organic 2 because it's just so much review of Organic 1. But it also gives you the reference of where you can go back and find those reactions if you need a little brush up. Now, the last reaction we're going to talk about, we're going to explore something called a Birch reduction. Reducing double bonds is something that you covered at length in Organic 1. You used hydrogen and some sort of metal catalyst, and you could reduce double bonds, you could reduce triple bonds all the way down to alkanes. Now, it's possible to reduce benzene this way, but look at this. It requires 150 degrees Celsius and 100 atmospheres of pressure. We call those forcing conditions. This would be not something that we could perform in a typical organic lab. That might be something that perhaps chemical engineers might handle in a plant environment. So what's nice about that is you can use hydrogen and palladium, hydrogen and platinum to selectively reduce. So if I take a benzene containing compound like styrene and I use just my regular hydrogen and platinum or palladium on carbon or nickel, whatever that catalyst is I use here other than Lindlar's, and I don't use forcing conditions, right? We're at about room temp, 2 atmospheres. It's a far cry from 100 atmospheres. We are going to easily reduce that double bond, but we leave the aromatic compound intact. And note, you get 100% yield there. So it really does not want to reduce the aromatic ring. And you should know that. Okay, so great. You told me we were going to do a reduction. We are. We're going to reduce benzene with using a little bit more creativity here. We're going to take benzene and we're going to treat it with sodium, methanol, and ammonia. This should look rather similar to your dissolving metal reduction, the way you could go from a triple bond to a transalkene, and the mechanism you're going to see has some similarities to that. It leaves us with a cyclohexadiene. Now, you could take that and you could treat that with platinum or hydrogen and a metal catalyst and get cyclohexane, or perhaps you want a cyclohexadiene. Now, I want you to look at this mechanism. While I'm not going to ask you to draw a mechanism, I may ask you questions about it. So it's still going to be important that you look through the mechanisms that I ask you to know about. This one is one of my faves because it allows us to use both the double-headed arrows and the single-headed arrows, much like that dissolving metal reduction. And we make all the intermediates. We make radical cations and radical cations. So what's the first step? Well, the reason that, and I always holler about this when we do dissolving metal reductions, you want to be real careful not to put the Na and NH3 too close together, because then that gets confused for sodium amide. You don't want a sodium ion. You want sodium metal because you want it to have that electron. You want it to be neutral because it will react with your benzene. You wind up, oh no, what am I doing? You don't form a bond. You give an electron to the ring. Now, you can't have more than 8 electrons. I'm going to zoom in so that I can draw these arrows. But what you're going to wind up doing is you're going to split this pi bond. One electron will stay on that carbon and form an ion, and the other one will shift. Notice I'm using single-headed arrows. Now, we can't have 5 bonds on this carbon down here, so this also splits apart. There's 4 arrows there, and it makes a radical, not cation, we're making anions, I'm sorry, a radical anion. So we wind up with those 2 up on top, new double bond here, radical at the bottom. As you might imagine, this is not particularly stable. And this anion's fairly basic, and it will deprotonate your methanol. That's why your methanol is there. It's your proton source. This leaves us with our second intermediate, which is just a radical. Well, you don't have to draw it, but there is a hydrogen there. There's a new hydrogen. Excuse me. And your radical. Now, your radical is not particularly stable either. And so you're going to donate another electron from a second atom of sodium. Sometimes when you see these, they might even put a 2 in front of the sodium in the reaction. In general, you are using excess of these reagents, so oftentimes you don't see the stoichiometry there. And then that leaves us with our final intermediate, an anion. So you go from radical anion to anion. And then in the last step, it's just another molecule of methanol. And that is going to leave you with your product. Now, the sodium is, I would imagine, primarily useful for like solubility. It's not going to be nearly as acidic as your alcohol. So you want to pull your proton from your alcohol. And then, of course, you can always refer to the slides for this mechanism as well. There's some additional notes here. It's primarily what I said as I was walking through it. There is one last issue that you have to deal with, and that's regiochemistry. I'm not going to walk through the mechanism again, but I am going to point to it, especially on this slide here. There are 2 different types of groups that can be on a benzene ring here that we're going to be interested in. There could be an electron donating group, like a methyl, electron donating. So your R groups are electron donating. What else might be electron donating? I think that you might run across some examples, and this we're going to cover in the next chapter as well. An OR group, even though oxygen is electron withdrawing, it can donate electrons through resonance, so it often shows up here as well. The other option, of course, would be that we would have an electron withdrawing group. The most common is going to be some sort of carbonyl here. Electron withdrawing. You don't tend to, I'm not going to ask you about halogens. They'd actually probably wind up in this group. But I'm going to stick to any of your carbonyl containing compounds. So you would have your ring on one side, carbon, double bond to oxygen. It could be attached to a hydrogen, an R group, an OR, an NH2, a halogen, right? Any of your carbonyl containing compounds. The reason I'm breaking it into these 2 groups is because they come out with different products when you treat them with birch reduction reagents. So let's jot these down real quick. That is not methanol, CH3OH, and ammonia. If you have an electron donating group, the double bonds will wind up in such a way that the electron donating group is on the double bond. An electron withdrawing group, however, will wind up on one of the new sp3 hybridized carbons. This, of course, will be important for product prediction. Now, why does that happen? Well, think about where the anion forms. All right, so you have a radical anion and an anion, and they are like at a 1,4 kind of position to each other. They're across the ring from one another. If you have a electron donating group in this top or bottom position, then it is going to cause more electron density to be donated to an already very negative anion carbon. So it avoids this, and this proton would add somewhere else. So that, for instance, the CH3 would be out here, and so it's never directly attached to the negatively charged carbon. Now, an electron withdrawing group, on the other hand, if we had a carbonyl here, something like this, we'll just make a little ketone, then it can actually help spread that electron density out on that negatively charged carbon. And so it winds up because it, stabilizes these intermediates, the major product would have the carbonyl on one of this top or bottom, one of the carbons that picks up new hydrogen. And of course, this is explained in the following few slides. And it's not even so much a major and minor product. One product is made, the other one is not. R groups, again, electron donating. And then for your electron withdrawing, you're most likely going to see some sort of carbonyl compound. Now, I do want to point this out. At the end of a lot of our chapters, there will be another section on spectroscopy. We have covered what we are going to cover on spectroscopy. I am not going to ask you any more spectroscopy questions until the final. So I will typically just skip these sections. We've talked about what we were going to talk about. It's just a little fun information about aromatic chemistry and nanotechnology. We're not going to cover that, but if you love organic, this is a fun little topic towards the end of chapter 17. Just wanted to see if there is any review. Oh, and that's the end of the slides. Apparently, I just kept putting new ones. All right, excellent. That is the end of chapter 17. Chapter 18, we're going to dive right into actually reacting with the carbons in the aromatic ring.